Alright, good morning children. We'll be doing chapter number 2, work, energy and power today. Okay, so in this chapter we have to learn three physical quantities. Okay, they are work, energy and power. So as I said in earlier classes, whenever you are learning some physical quantity, okay, physical quantity in physics, you have to learn first its definition. Two types of definition you have to learn. One is the sentence form definition, okay, and the other one is the mathematical definition. Clear? Then you will learn its units, SI unit and CGS unit, and third will be your application, means use of this mathematical expression or mathematical definition of this physical quantity, that is to do numericals. All right, so now without much wasting our time, let's begin with the first physical quantity, that is work. Now when we say work, generally we understand that the things that we do or the activities that we do in our day-to-day life is work, isn't it? Like washing our clothes, cooking food, writing or doing our assignments, learning, studying. These are all the work that we generally do, isn't it? But in physics, work is not understood in that concept. Concept of work in physics is different, is in a different form. In physics, work is done only when there is a force acting on an object which produces some displacement on the object. All right, so force and displacement, there should be force acting on the body, and this force must produce what? Displacement on the object. Then only we say work is done. So the sentence form of definition of work is: work is said to be done only when the force applied on the body, okay, makes the body move, that is, there is some displacement. Understand? Clear? Now let us learn about the mathematical definition of work. So here you see that more physical quantities are playing a role to explain force, that is work, that is force and displacement. Understand? So from this concept we get a relation that work is said to be done, or work is done, okay, when there is a force, okay, acting on an object produces some displacement. So when you multiply or find the product of force with the displacement, you get the amount of work done. So mathematically, amount of work done is the product of force acting on the body to the displacement that is created, okay, from the point of application of force to the direction of force. So W is equals to F into S. All right, so here you have two factors on which work done depends, that is force. Number one is force, number two is displacement. Clear? Now suppose you have a path from A to B and you have kept an object at point A and you are applying a force F on this object. So the direction of force is from A towards B, but the displacement takes place in some other way, in some other direction, that is from A to C. Let us take in this direction, this way. Okay, now from point C, if I drop a perpendicular on AB, I get a right angle triangle, and here displacement is making an angle, some angle with the direction of force, and let that angle be what? Theta. Okay, so now from here I know AC is displacement, but AB, I do not know how much is AB. So if I find from this triangle ABC, okay, from the relation cos of theta, okay, I'll get base by hypotenuse, or I'll get from here AB is equals to AC is how much? Displacement, that is S, so S cos theta. So here I get AB is my S cos of theta. So the amount of work here is A C into AB, isn't it? Arrange displacement to the component of force. So I'll get here, okay, there is a little error here. It's not like this. Okay, here it is force into AB, that is the component of displacement. So I'll get F into S into cos of theta. So I'll get the relation of W, that is F into S into cos of theta. Is that okay? Now, so here we got another factor, third factor on which the work, okay, on which the work done is depending, that is the angle between the force, direction of force to the displacement. So if theta is 0 degree, that's the angle between the displacement and the direction of force is 0. This is possible when both force, okay, and displacement are in the same direction, theta becomes 0. त्यति बेला चाहिँ W equals to F into S into cos of 0 degree, and you know cos of 0 degree means 1, so F into S into 1. So I'll get AW is equals to Fs or F into S. So this is one of the first equation, okay, that we have already learned, and this is taken to be as positive. So work done is positive, okay, when the direction of force to the displacement is 0 degree. Now what happens when theta is 90 degree? Okay, when theta is 90 degree, I'll get W equals to F into S into cos of 90. So 90 degree means the displacement and the direction of force are perpendicular to each other, that they are normal to each other. Then I'll get F into S into 0. Okay, because cos 90, the value of cos 90 is 0. So त्यति बेला चाहिँ work done is 0. So this is the condition when work done is 0, even when force is acting. Alright, clear? So work done is 0 when there is no displacement. Is that okay? Now if the displacement of the object is opposite to the application of force or the direction of force, then the angle between them is 180 degrees. So at this time I get W is equals to F into S into cos of 180 degree, which means F into S into minus 1. I'll get W equals to minus F into S. So this is the equation when the work done is negative, because I'm getting the relation in terms of negative sign here. Alright, so I get the equation W is equals to minus F into S. Is that okay? Alright, so here I got number 1 is W equals to F into S. Number 2 is W is equals to F into S into cos of theta, and I got W is equals to minus F into S. These were the three equations I got. But if you are doing the work against the gravity, means you are raising something up, okay, from the surface of the earth. Suppose this is the surface of the earth, you have taken one stone or anything, okay, and you are lifting it up and reaching here. So the force acting on this object is due to gravity, right? And now at this position, the force acting on it will be because of its own weight, that is W. W is equals to mg, that is how we get, isn't it? So here the force acting on this body due to its own weight is F is equals to mg, okay, and it has displaced from the ground to this height. So this is your displacement, that is the height, understand? So we get W is equals to F into S. So F here, the force acting on the body is due to its own weight, that is mg, and the displacement here is the height, that is m, that is h. So we get number 4th relation, that is W is equals to mgh, the fourth relation to find work done. All right, so okay, now after this what we have is the unit. What we must learn is the unit. Okay, unit of work. So unit of work, as I said, you'll have SI and CGS. In the SI system, the unit of work is joule. It is what? Joule. Joule, joule, abbreviated as capital letter J. Okay, and in the CGS, okay, in the centimeter gram, okay, second measure, it is what? Erg. ERG, erg. All right. Yes. Now you know the relation W equals to F into S. So we are saying that the SI unit of work is joule, and you know the SI unit of force is Newton, okay, into SI unit of displacement is meter. So if I write 1 joule, I'll get 1 joule equals to 1 Newton into 1 meter. All right, so I get 1 joule. So I can now define what is 1 joule. So definition of 1 joule. So 1 joule is the amount of work done when a force of 1 Newton is producing or displacing an object by 1 meter. All right, or you can define in the other way. Okay, when 1 Newton of force, okay, makes a displacement of 1 meter on an object, then the work done on that object is 1 joule. Okay, so similarly we can define 1 erg also. 1 erg also. So here we can write 1 erg equals to the CGS unit of force is dyne. So 1 dyne into 1 CGS unit of displacement is centimeter. So 1 erg, okay, 1 erg is the amount of work done by the force of 1 dyne. So the displacement produced on the body is 1 centimeter. All right. So today's first assignment is define 1 joule. Number 2, define 1 erg. Okay, clear. Now let's get the relationship between SI unit of, okay, work to CGS unit, or to its CGS unit. Now we know that 1 joule equals to 1 Newton into 1 meter. Okay, from here, isn't it? From here we got that, right? Is that okay? Now we can convert 1 Newton into dyne. 1 Newton means 10 to the power 5 dyne, okay, into 1 meter means 100 centimeter. Okay, it means 100 centimeter. So I get 10 to the power 5 into 100, I can write as 10 square, okay, dyne centimeter. So I get 10 to the power 5 into 10 to the power 2 is 10 to the power 7 dyne centimeter. But what is dyne centimeter? From here dyne centimeter baneko erg, right? So I get 1 joule is equals to 10 to the power 7 erg. Clear? So this is the relationship between SI unit of work, that is joule, to the CGS unit of work, that is erg. So assignment number 3 for today is derive, write it, derive the relationship between SI unit of work to its CGS unit, that is the relationship between joule and erg. That is what you have to find. Clear? Okay, so now 3 things, as I said you in the earlier I said that you have to learn definition, unit, and the application. So we learn definition of work both in the sentence form and in the mathematical form. And we also learned here the units, isn't it? We learned about the units, joule and erg, okay, and application of these relations, okay, we will do later in the class. All right, now let's go to the second physical quantity of this unit, that is power. Now what is power? In the sentence form, the definition of power is rate of doing work, okay, and in mathematical form you can write, okay, that power equals to W by T. T. So what is W? W is the amount of work done. So the ratio of work done with the time gives you the power. Alright, so here you see that the work done and time is required to express power. So these are the two factors now. So the two factors on which power spent by a source depends are amount of work done by the source and the time taken by the source to do the said work. Okay, so the next assignment for today, number 4th assignment, is factors which on which power spent by a source depends. So write the question number 4. Okay, state the factors on which power is spent by a source depends. So the answer will be the power spent by a source depends on the following two factors. Number 1, amount of work done by the source. Number 2, the time taken by the source to do the work. Alright, so this is your assignment number 4. Now after this you must learn the units. We have learned the two definitions here. Rate of change of doing work is called power. Mathematically, power is equals to W by T. We saw both the definitions, isn't it? Now let's learn the unit. Now power equals to W by T. This is our mathematical definition. So W, that is work done, is expressed in a unit called joule, okay, in the SI, and time in second, isn't it? So joule per second. So joule per second is the unit, but instead of this we use the unit called watt. Every bit is capital letter W. So the SI unit of power is watt, and CGS unit is erg per second, because the CGS unit of work is erg, and the unit of time has only one unit, that is second. Okay, so erg per second is the CGS unit of power. Is that okay? Yes. Okay, similarly you have to learn about bigger units also, okay, which we have been learning: kilo, mega, gigawatt, isn't it? Yes. So kilowatt, you have bigger units. Then you have megawatt. So see the difference how I have written: kilowatt, small k, capital W; megawatt, big K, small w, okay, and gigawatt. And you must also know their relation. 1 kilowatt equals to 10 to the power 3 watt. 1 megawatt equals to 10 to the power 6 watt, and 1 gigawatt equals to 10 to the power 9 watt. So please remember this. Understand? Is that clear? Now apart from this, you also have one more unit which is called as horsepower. This is the unit of power. Okay, understand, this was used in earlier days when we had horses, isn't it? So एउटा घोडाको शक्ति बराबर भनेर नाप्थ्यो पहिला. So horsepower. Alright, so horsepower is another unit of power which is largely used in mechanical engineering. Mechanical engineering भन्दाखेरि चाहिँ the one which produces mechanical energy, like your bikes, cars, trains, okay, now your mixer, grinder, washing machine, all the appliances which converts electrical energy to mechanical energy, or which gives you mechanical energy. So horsepower is another unit of power. So it is a unit of power which is generally used in mechanical engineering. Okay, clear? And this relationship between horsepower and joule. Okay, so 1 horsepower भनेको चाहिँ कति joule भन्दाखेरि चाहिँ it is sorry, not joule, it's watt. Okay, horsepower भनेको चाहिँ कति watt. If that question comes, then 1 horsepower is 746 watts. So please note this down, very important relations, because we'll be using this to do some numericals later on. All right, okay, now let's move forward. So we see the heading, if you remember, it was power. If you remember the heading, it was work, energy and power. That was the heading of unit A. We have learned about work, we have learned about power. Now we are left with energy. Now what is energy? Energy, it means capacity of a body to do work. Okay, this is the definition of energy. Energy is the capacity of a body, okay, of a body to do work. कुनै पनि बडीको काम गर्ने क्षमतालाई चाहिँ भन्छ energy. Understand? Is that okay? But in physics, what we will consider is that you spend energy to do work. So somehow work is done only when you are spending some energy. Okay, so energy spend गरे भने चाहिँ you will get some work. So that is why they are somewhat similar to each other. So that is why we use the same unit. Okay, so the unit of work was joule. Similarly, unit of energy is also joule in the SI system. Unit of work in CGS system was erg. Similarly, unit of energy is also what? Erg. Okay. Now, apart from these two units, you have other bigger units of energy. Okay, other bigger units of energy. So let's learn them. Okay, number one is watt. Okay, hour. Watt hour. Number two is kilowatt hour. Okay, and number three is calorie, and number four is electron volt, EV. This is how we write the symbol for electron volt. So these are all the units of energy. Are you getting my point? All the units of bigger units of energy. Energy ko SI unit is joule, but bigger units is watt hour, kilowatt hour, calorie, and electron volt. All right. So you'll get the definitions and relation in your book. So please go through it. Okay. I will just read. Okay. I'll just dictate the meaning of watt hour. So 1 watt hour, what is 1 watt hour? It is the energy spent or work done by a source of power of 1 watt in 1 hour. So energy is spent by a source of power 1 watt, because watt is the power, a unit of power, hour is the unit of time. So 1 watt चाहिँ 1 घण्टामा चलायो भने चाहिँ that energy is called watt, 1 watt hour. Similarly, kilowatt भनेको चाहिँ 1000 watt in 1 hour. So if a source is spending 1000 watt in 1 hour, then the energy spent at that time is 1 kilowatt hour. Clear? Similarly, another one is calorie. This is the most commonly used unit to express heat energy actually. Okay, you will find this calorie or kilocalorie, okay, KCL, written on the food packets ma लेखेको हुन्छ. So when you consume that food, what amount of energy, heat energy is going to supply you. So calorie and kilocalorie are the unit of commonly used unit of heat energy. Understand? Then the other one is electron volt. What is electron volt? Electron volt is the energy possessed by tiny particles like at electrons, okay, protons and neutrons. When the charged particles, basically charged particles, the energy carried by charged particles is measured in electron volts. Okay, clear? So you must remember the relation of watt hour with joule, relation of kilowatt hour in joule, relation of calorie in joule to the joule, relation between electron volt and joule. So please note this down. It's important for your numericals. Okay, so 1 watt hour equals to 3600 joule. Okay, this is number A. Number B is 1 kilowatt hour. 1 kilowatt hour. So watt कोही ठुलो चाहिँ किलोवाट भयो नि त. So kilowatt is 1000. So 3600 multiplied by 1000 will give you kilowatt hour. Understand? So this you can write as 3.6 kilojoule. Okay, this you can write as 3.6 into 10 to the power 6. Okay, 10 to the power 3.6 into 10 to the power 6 joule. So 1 watt hour, kilowatt hour means 3.6 into 10 to the power 6 joule. Number C was your calorie. 1 calorie equals to 4.18 joule, which we write in excuse me, approximately we write it as 4.2 joule. All right, then number D is 1 electron volt. 1 electron volt equals to 1.6 into 10 to the power minus 19 joules. It's a very small amount of energy. Clear? So please remember, note this down in your copies as well. 1 watt hour equals to 3.6 kilojoule, or you can write this as 3.6 into 10 to the power 3 joule. Okay, 1 kilowatt hour is equals to 3.6 into 10 to the power 6 joule. 1 calorie is equals to 4.2 joule, and 1 electron volt is equals to 1.6 into 10 to the power minus 19 joule. So please note down all the relations for energy, relations for power, bigger units, okay, as well as relationship between HP, horsepower, and the SI unit of power, that is watt. And also do remember this relation of bigger units of energy, that is watt hour, kilowatt hour, calorie, and electron volt. All right, so this is it for today. In the next class we'll be doing some numericals, that is the application part. Okay, so today we learned about power, energy, and work, its definitions, its SI units, its measurement, its relationship between SI units and CGS units. We also learned about bigger units, isn't it? Now we are left with application of this mathematical mathematical statements of power, work, and energy, and that we will do in the next session. All right, okay, thank you.